Welcome to the Explainer. Today, we're going to pull back the curtain on the hidden mathematical rules that, believe it or not, run just about everything. We're talking about the secret code that governs your ATM, your phone, and even the entire economy. And it all starts with a pretty simple question. Okay, so think about it. A clock goes through 12 hours, then it just resets and starts over. A traffic light cycles through red, yellow, green. Same thing over and over. Even your phone's lock screen uses these predictable patterns. Now, these things seem totally unrelated, right? But they're actually all marching to the beat of the same hidden mathematical drum. You see, the secret here isn't about what these things are, but about the invisible structure they all follow. The best way to think about it is like a kind of mathematical DNA, a fundamental set of rules that dictates how a whole system behaves, whether that system is made of numbers or lights or little metal gears. And this idea brings us to a field of math called abstract algebra. Now I know, don't let that name scare you off. It's not really about doing complex calculations. It's actually the science of studying these hidden rule systems themselves, that mathematical DNA we've been talking about. So to make this easy, let's imagine we're visiting 3 different villages, and each one has its own set of laws. Our first village is called a group. Life here is simple. You can only do 2 things, add and subtract. That's it. This is the perfect system for, say, an ATM. You put money in, that's addition. You take money out, that's subtraction. Nice and simple. All right, now let's wander over to the next village. This one's called a ring. Now, they've got all the rules from the group, so you can still add and subtract, but they've added a powerful new tool, multiplication. Suddenly, you can do more complex stuff, like a shop owner figuring out the total cost for 5 items that are $10 each. Things are getting a little more sophisticated. And our final stop is the most powerful village of all. It's called a field. This place has the whole shebang. It's got addition, subtraction, multiplication, and it finally adds the last piece of the puzzle, division. With this complete toolkit, you can now tackle really complex problems, like the formulas a bank uses to calculate compound interest. So here it is, all laid out nice and neat. You can see the progression so clearly. A group is the foundation. A ring is just a group that also has multiplication. And a field is just a ring that also has division. Each one builds on the last, adding a new power. This right here is that mathematical DNA we're talking about, in its purest form. But here's the crucial thing to understand. These villages, they're not just some weird abstract idea. No, they are the actual real-world blueprints for tons of systems that you and I interact with every single day. And that's really the big mental shift here. Abstract algebra pushes us to stop looking at all the individual numbers and to start focusing on the underlying system, the rule book that controls them. Because once you understand the rules of the game, you understand everything that can possibly happen in that game. And this is where it all clicks back into the real world. That ATM you use, it's operating in a group. The accounting system at your local store, that's a ring. The bank's complex financial models, they need a field to work. And it goes even deeper. The cryptography that keeps your data safe online, or the QR codes you scan with your phone, they all rely on these strict, predictable mathematical structures to be secure and reliable. It's wild. Okay, so those structures are perfect for describing systems that are pretty much fixed and stable. But what about systems that are constantly in motion, always changing over time? How does math deal with that? Well, that's where we need to bring in a different but totally related set of mathematical tools. And that question right there leads us to another incredibly powerful part of math, one that honestly works almost like a crystal ball. It lets us peek into the future of systems that are in constant motion. So to see how this works, let's dive into a simple story about 2 villages. Every single year, a bunch of people move between them, which creates this dynamic, always changing system. The rules for this migration are super simple and they never change. Village A is a little more popular, so it holds on to more of its residents. Village B, on the other hand, loses a slightly bigger chunk of its population to Village A each year. And believe it or not, these 2 little rules are all we need to predict the entire future of these villages. So let's say we start out with 100 people in each village. After just 1 year, those migration rules kick in. Village A grows to 110 people, while Village B shrinks down to 90. The system is officially in motion. Now let's fast forward 5 years. The trend is pretty obvious. Village A keeps growing, Village B keeps shrinking. But what's really happening under the surface is that the whole system is slowly but surely moving toward a point of balance. Then, after about 20 years, something really remarkable happens. The change just stops. The populations lock into this perfectly stable state, 200 people in Village A and 100 in Village B. And no matter how many more years go by, that perfect 2-to-1 ratio is going to stay exactly the same. The system has found its equilibrium. But here's the absolute kicker. This final outcome, it wasn't a surprise, it wasn't random chance. It was mathematically guaranteed from the very second we set those migration rules. It was hiding in the system's DNA the entire time. So how in the world could we find that hidden destiny without having to wait 20 years? Well, math gives us this incredible tool. It can identify the one special hidden direction inside a system, the one direction where all the change is just about getting bigger or smaller, but the core ratio never changes. That special direction is called an eigenvector. You can think of it like the system's own internal compass, and it's always pointing toward its most stable state. For our villagers, that hidden compass was pointing right at a 2-to-1 ratio, and the system just followed that path until it got there. And this predictive power isn't just for some imaginary villages. This exact same mathematical logic is used to model incredibly complex systems in science, in ecology, and in finance. I mean, check this out. On one side, you've got an ecologist modeling a toad population to figure out if it's going to survive long term. On the other side, you have an economist modeling how money flows between industries to predict economic balance. The problems seem completely different, right? A toad is not a dollar, but the mathematical tool they both use to find that stable endpoint, that eigenvector, is exactly the same. So, after all that, what's the big takeaway? What's the new lens this gives us to look at the world? Is this really profound and powerful idea that so many parts of our world that seem chaotic and messy, like population changes or the movement of money, are actually governed by these deep, discoverable, predictable mathematical laws. This math gives us a universal language to understand those hidden structures and even to predict what's coming next. And once you learn how to look not just at the things themselves, but at the rules that connect them, you really do start to see these hidden patterns everywhere. From the algorithm on Facebook to how our financial systems work, it's all being guided by this secret world of math. So the only question left is, where are you going to see it next?